The electrochemistry laboratory at Uam-Iztapalapa is one of the most renowned in the country. It was born in the heart of Iztapalapa, one of the most traditional and populated zones in Mexico City. The Electrochemical Energy Storage Laboratory was founded in 2013 as a new division within the chemistry department, but with a multidisciplinary vision. Our main objective is to develop Mexican technology in the area of energy storage for a more sustainable future. Among the many options for energy storage, electrochemical batteries, and especially lithium-ion batteries, stand above due to their excellent energy density, power, and high voltage. We are interested in all areas, but mostly in developing new chemistries for cathodes, anodes, and electrolytes, new binders and conductive additives, testing and cell manufacturing. Different strategies are used for battery chemical components preparation. The control of temperature ramps, final temperature, time and cooling rates are needed to ensure the attainment of the desired structure and inclusion of cation and anion dopants. Some syntheses require the presence of specific oxidant or reducing atmospheres, for which a controlled flux of gases is directly forced in the laminar regime towards the system. Other techniques, such as coprecipitation, colloidal and electrochemical synthesis, are used when needed. Still, other methods are used for pre- and post-treatments, such as high-energy ball milling, to mix precursors, control the size, and ensure the dispersion of components. Also, this method is used to create multi-phase blends for special applications. For polymers, we employ several techniques, such as jellification, single conduction polymerization, and in situ binder polymerization for the single-step formation of electrodes. State-of-the-art characterization techniques are used to corroborate the chemical and physical properties of the synthesized materials, either of those recently synthesized or post-operation samples. IR and UV spectroscopies, along with powder XRD, are among the most commonly used to corroborate the nature of the phases, changes in the composition, doping, and phase interactions. Size and morphologic changes are controlled by chemical and physical methods, while the structure is determined by electron microscopies, SEM and TEM, in the microscopy laboratory at Uam-Iztapalapa. One of the most critical aspects of batteries are local chemical changes, which change the mode of interaction of lithium or any other ion within the crystalline structure. Nuclear magnetic resonance in solids is a powerful tool that has been very helpful in determining the changes associated with doping, functionalization, changes in salts, and polymers coordination, and also some ex situ experiments of the intercalation mechanism. Other techniques used in collaboration are XPS to detect oxidation states of metals, electron paramagnetic resonance, and Raman spectroscopy to detect changes in coordination. In addition, we have all the electrochemical machinery from multi-channel potentiostats, special electrochemical impedance channels, and battery cycle for many cell configurations, to high power sources and several cell configurations for testing. However, one of the main landmarks of our laboratory is the in situ analysis of materials. We have realized that the determination of the changes occurring during battery operation is fundamental. Thus, we have developed methods to analyze the structural changes in the active materials by XRD. These changes are originated from continuous cycling, the effects of the potential, and the specific conditions of operation. Our cell has special windows capable of being conditioned to analyze other sources like Raman or IR radiation. Furthermore, the analysis of gases produced by the in situ operation is possible by a mass spectrometer coupled to the electrochemical cell. The control of gas production is one of the most important areas for side reactions determination and for safety and durability of batteries. Electrochemical impedance can be categorized as another in situ technique. This laboratory has developed techniques using 3 electrode cells capable of discerning the effect of different binders, cathodic and anodic materials, electrolytes, and operating conditions. firmly believe that the incorporation of materials into real systems is mandatory. We have been fortunate enough to have the funding to gather all the equipment necessary for assembling coin and pouch cells. Some of the many control stages are mixing, which is a fundamental stage aimed at providing a perfect contact among the components. Equipment for coating and drying, cutting in different sizes, calendaring at controlled spacing and temperatures, fundamental for good adherence, equipment for coin cell preparation, and pouch cell assembly, including vacuum sealing, welding, and filling the electrolyte. Conditions for handling reactants and all the materials contained would be impossible without special equipment. Our glove box is capable of sustaining water and oxygen conditions lower than 0.5 ppm. The glove box is used for all chemical compounds requiring special handling. However, for unspecific conditions, other dry equipment and small glove boxes are employed. And last but not least, we want to underline that our most important assets are our graduate and undergraduate students and postdocs. Very intelligent, hardworking and dedicated people whose help and commitment have made us grow not only in capacity, but also in knowledge.